Once the inverse trig functions are developed and we looked at what the restrictions on the domains of the original trig functions needed to be so that our function would be one-to-one and its inverse would also be a function, the restriction on the domains that we had to do to get that one-to-one span for our trig functions are a restriction on the range of the inverse trig function. I developed that in a previous video, and the link to that is in the description of this one. Just to recall what happened is written up here so that we can reference it when going through these examples. So first, for y equal inverse sine of x. Well, the original sine function's domain needed to be restricted to negative pi over 2 to pi over 2 to get that span where the sine function was one-to-one, and also would have the outputs through all of the values that the outputs would give. And so the restriction on the domain in the y equals sine x function gave us a restriction on the range of the inverse sine x. So for y equal inverse sine of x, its inputs are ratios, and the ratios are from -1 to 1 because that was the range of the original sine function. And then the range of the inverse sine function is what the restrictions were on the domain of the original sine function, and that was from negative pi over 2 to pi over 2. So remember, when you have a one-to-one function and you find the inverse function of it, the domain of the original function is the range of the inverse, and the range of the original function is the domain of the inverse. They switch because you switch the x's and y's. And also remember that idea of an inverse function. It is the function that undoes what the original function did. In trig functions, you put in an angle and it gives you out a ratio. So the inverse trig functions take in a ratio and give you back an angle. For y equal inverse cosine of x, we needed to restrict the domain of y equal cosine of x from 0 to pi. And then that became the restriction on the inverse cosine function. So for the input for inverse cosine function, it's from -1 to 1. And for the output for the inverse cosine function, it's from 0 to pi. And then for y equal inverse tan x, the input is all real numbers, and then the output is between negative pi over 2 and pi over 2. It doesn't include the negative pi over 2 and pi over 2 because the original tangent function had vertical asymptotes there. When we're doing these, if we have the inverse trig function acting on a ratio that came from a nice angle, then we want to answer those questions with those exact angles. If we're taking trig functions of inverse trig functions or inverse trig functions of trig functions, we want to work from the inside out, just like we do with nested parentheses. And if we're working with an expression that requires a trig identity in order to get it to the point that we could finish it off, we need to recall those. Our first one is inverse sine of the square root of 3 over 2. So when we see this, I want to refer to the inverse sine and remind myself of what the range of values I can answer in, and then think, what angle in the span from negative pi over 2 to pi over 2 has a sine ratio of the square root of 3 over 2? Well, that angle is a nice angle, and it's pi over 3. In part B, we're looking at inverse tan, and for inverse tan, I have to give my answers between negative pi over 2 and pi over 2. So what angle in the span between negative pi over 2 and pi over 2 has a tangent ratio of -1? Well, I know all of the first quadrant angles had ratios that were positive. So if I'm going in the span between negative pi over 2 and pi over 2, I need to think about, back to the unit circle, reaching down into the fourth quadrant to get an angle whose tangent ratio is -1, and that happens at -π/4. So you can think through reference angles. The reference angle whose tangent ratio is 1 is π/4. But to get it where my tangent ratio is -1, I have my -π/4 because of the specified range we have here. Next up is arc cosine. So be careful with arc cosine or inverse cosine. Its output range is 0 to pi. So when I think what angle in the span from 0 to pi has a cosine ratio of -2/2? Well, again, that's a reference angle of π/4 that would have a cosine ratio of √2/2. But to get the cosine ratio to be negative, and in the span from 0 to pi, I would be in the second quadrant if I was thinking of the unit circle. And so that angle would be 3π/4. How about arc sine of -1? What angle in the span from -π/2 to π/2 has a sine ratio of -1? Well, that would be at -π/2. And notice I can't do 3π/2 because 3π/2 is not in the span from -π/2 to π/2. It's too big to be given as that span that we're allowed to do as a output for the inverse sine function. Okay, now here's where we start finding the trig function of an inverse trig function, or in other problems, the inverse trig function of a trig function of an angle. So start from the inside out. What angle in the span from -π/2 to π/2 has a sine ratio of -√2/2? Well, that'll be -π/4. And then we're going to take the tangent of -π/4. And the tangent of -π/4 is -1. How about the next one? Here, it's the inverse sine of the cosine of 5π/6. So start from the inside and work out. So we're going to have inverse sine of, well, the cosine of 5π/6 is -√3/2. And then I think, what angle in the span from -π/2 to π/2 has a sine ratio of -√3/2? Well, that's going to be a reference angle of π/3, but I need it in this span from -π/2 to π/2, so that's going to be a -π/3. Next up is the tangent of the arc cosine of 5/13. Now here's the first time where I wasn't given a question where I have an inverse trig function of a ratio that would lead me back to a nice angle. I don't have an angle within my special angles that would have a cosine ratio of 5/13. So when that happens, I want to make a right triangle. And remember, the output span for the inverse cosine function is from 0 to pi, but this is the inverse cosine of a positive ratio. So I'm going to draw a right triangle that is a first quadrant angle. And inverse cosine functions, inverse trig functions in general, have ratio in, angle out. So this is an angle. The arc cosine of 5/13 is an angle. And it's the angle in standard position for the trig angle. So this actually written all the way out is arc cosine of 5/13. But remember, the cosine ratio is the adjacent side over the hypotenuse. And since this is the angle whose cosine ratio is 5/13, that means the numerator 5 is the adjacent side, and the denominator 13 is the hypotenuse. And now I can use the Pythagorean Theorem to find the missing side of the triangle, and always be very cognizant of where your triangle is drawn into, so that you make sure when your x-coordinate is right, it's positive, and when your y-coordinate is up, it's also positive. But if I needed to draw either in the fourth quadrant or the second quadrant because of the different specified ranges, then I would need to say that if I'm going left with my x, that's going to be where the negative value goes. Up is positive. If I'm going right, it's positive, but if I'm going down, then negative. So always keep aware of that. Well, using the Pythagorean Theorem, I have 5 squared plus y squared is equal to 13 squared. So that's 25 plus y squared is equal to 169. Subtracting 25 from both sides, you get y squared is equal to 144. And when you take the square root of both sides, we normally would say don't forget the plus or minus. But I know its y coordinate is up, so positive, so my y is positive 12. Now, I want the tangent of this angle. So read the tangent off of this angle, and tangent ratio is opposite over adjacent, so 12/5. All right, how about the cosine of the inverse sine of -3/5? So I'm going to draw my sketch again. Inside out, I have the inverse sine of a negative ratio here. So this is the angle whose sine ratio is -3/5. Well, in our span, but from -π/2 to π/2, the sine ratio will be negative if we're looking at it being in the fourth quadrant. So I can draw my right triangle this way. And then here is the inverse sine of -3/5. Remember, the sine ratio is opposite over hypotenuse. So for my inverse sine of -3/5, the numerator -3 is on the vertical portion of the right triangle. The 5 is the hypotenuse. And when you do the Pythagorean Theorem, you'll get our x squared plus -3 squared is equal to 5 squared. So x squared plus 9 is equal to 25. X squared is equal to 16. But when I take the square root of both sides, remember to do the plus or minus, but think through it. I'm going right, so I'll use the positive 4. So x is equal to 4. Now, read the cosine off this angle. The cosine of this angle is adjacent over hypotenuse, so that's going to be 4/5. And then lastly, this is the sine of 2 times the inverse cosine of 4/5. Well, remember, the inverse cosine of 4/5 is an angle, so this is the sine of twice an angle. Now, if I think back to the sine of 2 times an angle, that has a trig identity. And you can look back to your trig identity rules, or remember that the sine of 2 times an angle is 2 times sine the angle times cosine the angle. So 2 sine A cosine A is the identity that we need to use for this particular thing. So taking this back to my A being the inverse cosine of 4/5, I have 2 times the sine of the inverse cosine of 4/5 times the cosine of the inverse cosine of 4/5. And again, I'll also put a link to a video of the trig identities in this description if you need a review of those. Now, 4/5 is not a ratio of a nice angle when we look at these for the inverse cosine of 4/5. So we're going to draw our right triangle. It's a positive ratio, so we're going to draw it into the first quadrant. Here's my inverse cosine of 4/5. That's adjacent over hypotenuse, so 4 is adjacent, hypotenuse is 5. When you do the Pythagorean Theorem, and it's up, so it's positive 3. So this is 2 times. The sine of this angle is opposite over hypotenuse, so 3/5. And then times the cosine of this angle is adjacent over hypotenuse, so 4/5. And when we multiply these all together, 2 times 3/5 times 4/5, well, 2 times 3 is 6 times 4 is 24, and in the denominator, 5 times 5 is 25. So we get 24/25.